So students will see the benzene molecule and in which resonance how takes place. Okay, so just now we discussed the resonance means the interchange of different structures of one molecule. Okay, of a molecule into one structure into another by change in position of pi bonds. Sometimes pi bond with pi bond and sometimes pi bond with a lone pair or a pi bond with a negative charge also. Okay, so benzene. Example, if you take a benzene, the benzene formula is C6H6. Okay, now we will write its structure in line formulae. In line formulae means here we have to show the molecule with corners and lines. So remember, in line formulae, each corner indicates a carbon and each line indicates a bond. So between the two corners, if it is a single line is there, means a CC single bond, and between the corners of these carbons, if a double bond, you see the two lines, means it's a double bond. Okay, so see here, this is CC single bond and this is a CC double bond. So now this is what seen in conjugated pi system. So means the two double bonds are, means the double bonds are separated by a single bond, must be separated by a single bond. Okay, so this is double bond, single bond, double bond, and this is one. And remember, in line formulae we can't see the carbons and hydrogens. So means each corner is a CH. So this is what Kekulé structure 1, because the structure of benzene was explained by so many people like Armstrong, what it is Prayers, and what it is Deva structures and Kekulé. So out of this, the whatever structures we use nowadays is what Kekulé structures. I call scientist Kekulé. So it is one structure. So if anybody is asked to write a benzene structure, so they write this name, write this formula, or write this structure. And suppose in a class, group of students will be there. One student writes this structure. Okay, it is one type. And for benzene, another student may write this structure also. This structure also. See here, it is also benzene with alternated double bonds. Okay, the both structures are same if you see. So the first is, let it Kekulé 1 and the next is Kekulé 2. Both are same, but if you keenly observe that these two structures are different, because in first structure, if you give the numbering to the each corner, that is carbons. See here, this is first carbon, second carbon, third, fourth, fifth, sixth. Okay, here also 1, 2, 3, 4, 5, 6. Okay, so in first structure you can see that the double bond or pi bond in between 1 and 2 carbons, whereas in second structure between the 1 and 2 carbons there is no pi bond, there is no double bond, only single bond. So in the same way between 2 and 3, okay, 2 and 3 carbons single bond, but here in the second structure between the 2 and 3 carbons there is a double bond. There is a double bond. So like that, what happened here from structure 1 to structure 2. Okay, the two different structures are there. Okay, one is Kekulé 1, other is Kekulé 2 structure. Okay, these both the structures belong to single molecule called benzene. Okay, so these two structures are interchangeable, interconvertible structures. See, I have used a special arrow which is having the head. So this is what known as arrow head. So a double headed arrow is used. This indicates that both the structures are interconvertible. Okay, means the first structure changes to second changes to first. So whenever any reaction or any two structures are interconvertible and both exist together, in that case the system is called as equilibrium. So these two structures of same molecule, which is benzene, both are existing. Then how these structures, one structure changes to second structure? This is what? By delocalization of pi bonds. The change in position of pi bonds. So the pi bond which is present between the 1 and 2 shifted to 2 and 3. And here which was present, see, in this way, and this pi bond which was present between the 3 and 4 shifted between the 4th and 5th, and which was between the 5th and 6th shifted to 6th and 1st. So by change in position of pi bonds, the first structure of benzene change into second structure. Then the same way, once again these structures, okay, from second structure also this pi bond will move in between the 1 and 2 carbons, and from 2 and 3 to 3 and 4, and once again 5 or 3 to 5 and 5, 4 and 5 to 5 and 6. So like this process, change in position of pi bonds continuously takes place. And this continuous change in position of pi bonds, when the pi bonds or double bonds are in a conjugated system. Conjugated system means where two double bonds are separated by a single bond. Okay, so in a conjugated system, always the interchange of pi bonds takes place, and sometimes the pi bond will change with a lone pair of electrons or negative charge. Okay, so why this happens? Because any molecule or any compound which has only single bonds, means only sigma bonds, that is very highly stable. Because we all know that between two atoms the sigma bond is formed by thorough overlapping, strong overlapping, end-on overlapping along the internucleus axis of both the binding atoms. The atomic orbitals or hybrid orbitals overlap completely to share the electron. Since overlapping is strong, the sigma bond is strong. So once a molecule contains sigma bonds only, which is strong, so the breaking of such bond required more energy. So in that case, under normal conditions, a molecule which contain only sigma bonds, it do not react, because the normal condition energy is insufficient to break that sigma bonds. Therefore, any compound which contain the only sigma bonds will not react easily, means their reactivity is less. For example, alkanes. Okay, alkanes like methane, ethane, propane, butane, you know that, etc. So in this you find that between the two carbons only CC single bond, and between the carbon and hydrogen only CH single bond you find. Therefore the alkanes reactivity is less, hence they are called as parafins. But in case of alkenes and alkynes, in alkenes you find between the carbons CC double bond with 1 sigma and 1 pi. In alkynes, between the carbons you find triple bond, whereas 1 sigma, the remaining 2 between the carbon is a pi bond. So as the number of pi bonds increases, the instability of molecule increases, because pi bond is weaker bond. Pi bond is a weaker bond because during pi bond formation there is no complete overlapping of orbitals takes place. Okay, just sidewise overlapping takes place, which is improper, incomplete overlapping. So therefore the pi bonding electrons at any time they can be broken, they can be disturbed. That's what the pi bonding orbitals are called as delocalized orbitals. Means their position is not exact. As the pi electrons are moving around the nuclei of both the atoms, the pi bonds can change their position if they are in conjugation. Like if the two pi bonds are separated by single bond, then there is a chances of a change in position of pi bonds one with another. So in the sequence, one structure changes to another structure, and this phenomenon called as resonance. So here, to change its position, some energy is utilized, because when the molecule itself doing some work, doing some exercise. What is that? The position of pi bonds is changing. So for this change in position also the molecule needs some energy. So for this we need not to supply energy, as we know that pi bond itself is unstable. Pi bond itself is unstable means it is associated with more energy. So here the benzene molecule uses 36 kilocalories. 36 kilocalories per mole. 36 kilocalories per mole means per one molecule about 36 kilocalories of energy is utilized by itself, which is present in its own. Okay, so whatever extra energy is there, what is that energy? 36 kilocalories of energy was there extra. So by using this energy, the pi bonds will shift. So by using this 36 kilocalories of energy, the Kekulé 1 structure of benzene changes to Kekulé 2 structure. So whatever energy is used for the converting resonance structures, okay, one structure into another, is known as resonance energy. So you can easily remember that the resonance energy of benzene is 36 because C6S6. In the formula you can see that 2 6. So 6 6 36. You can easily make out. And this type of resonance, also we can see in oxo anions. In ozone also we can see that. In ozone also we can see. So see, what is the formula of ozone? I hope you all know that ozone is O3. Ozone is O3. So see here, in ozone 3 oxygens are present. 3 oxygens are present, and we all know that the oxygen is 6th A group. 6th A group means in the outermost shell of oxygen, that is valence shell of oxygen, the oxygen contain 6 electrons. So how many electrons are required to get the stability for oxygen? 2 electrons, because they are already having 6 electrons, and by getting 2 electrons, with each atom oxygen will become octet. So therefore it attains stability. So now see here, say this is first oxygen, okay, around which we have 6 electrons. Now here also third one I kept, and next here, okay, now 3 oxygens are there. Now each one is having 6 electrons on each. So here say the first oxygen, second oxygen shares 1 electron, means the 2 electrons of the second oxygen are shared with the 2 electrons of first. So 6 plus these 2, the first oxygen gets a octet. 6 plus these 2, octet. Okay, no loss, no gain of electrons, pure covalent bond. Okay, of course the first is sigma, second is pi. And next around this second carbon also, middle carbon also, it was having 6 electrons. By sharing of 2 electrons with this first carbon, it is getting a octet. So both are happy. But in ozone, how many oxygen atoms are there? 3 atoms. So now when this second oxygen is going to combine with this oxygen, now tell me how many electrons will be around this oxygen? See here, if it is using its 1 electron with the third oxygen, already having 8 electrons, with 1 electron of third will become how many? 8 plus 1, 9 electron. 9 electron, which is unstable, means it is no more possible because it is more than octet. So here what happens? This second carbon oxygen is using its 2 electrons, and the 2 electrons of second oxygen are used for bond. So here the second oxygen acts as a donor, because it is donating a pair of electrons which is equal to bond. So the second oxygen is a donor, and third oxygen is not donating any electron but sharing the electron from the which is taken by the second oxygen. So here between this second oxygen and third oxygen there is a coordinate covalent bond is formed, where second oxygen is donor, third oxygen is acceptor. Third oxygen is acceptor. So because of this, what we see that this second oxygen is losing electron. Second oxygen is losing electron. So on the second oxygen, we can write plus charge, and on the third oxygen, as it is getting the electron, negative charge. So this third oxygen not using any electron. So I'll write all the 6 electrons as it is. And next here on the middle oxygen only one pair is left, and here this first one and second, just pure covalent bond, no loss, no gain. And here the 2 pair of electrons on this first oxygen atom. It is what? One structure of a first structure of both are same. In first case I have used arrow mark. The arrow mark indicates that the direction of donation of electron. Second oxygen is donor, where third is acceptor. The tail of arrow indicating donor atom for the coordinate covalent bond. The head indicates the acceptor of the coordinate covalent bond. So the same it is. If you don't use arrow, you have to use plus and minus. Since donor donating electron, losing one electron. Acceptor gains an electron, negative charge. So both are same structures. Now for the ozone, we can write one more structure. So these two are same only. We are going to write second structure. So see, in second structure, I am using this blue pen. Same 3 oxygens, 1, 2, 3. Same as it is. Okay. This time, first, second, third as it is. So let okay, this is 6 electrons, and these are 6 electrons. Okay, these are 6 electrons of valence shell. So between the second and third, there is same as it is what we have seen in the first case. That is a double bond is there. So by sharing of electrons, so 6 electrons and 2 electrons of middle one, 8 electrons around this oxygen. And next here, once again what? In previous case we have seen that third oxygen was acceptor, and this time first oxygen is acceptor. Okay, so this third one is not using any of its valence electron to make bond with the second oxygen. The both electrons of second are donated by second oxygen to make the bond. So what is this one? Coordinate covalent bond. So here see, around this middle carbon, around this oxygen, how many bonds you can see in whether it's first structure or second structure? How many bonds you can see? 1, 2, 3. So total bonds, how many around this? 3 bonds. Okay. Now, but are these two structures are same? No. In first structure, the first oxygen is having double bond. In a second structure, the second is a normal, the third oxygen is having a double bond. So structures are different, but molecule is same. So these are what? Resonance structures. And the same thing I can write as here. Okay, this is without arrow, we have to use plus and minus. So the middle one is losing electron plus, and this one is what? Gaining electron minus, and it is not using any of the electron valence shell electrons, and this is double bond, and here 2 electrons, and this is. So here see, it is ozone is one molecule but shows 2 different structures, and these 2 structures are interconvertible. The first structure changes into another by changing their position. Changing their position means if okay, I will remove this. I'll remove this. So if see here, if this lone pair of any of 3 lone pairs, if any of this lone pair shifted in between this second and third oxygen, then what happens? Around this oxygen, how many valence electrons will be there? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, which is impossible. Therefore, what happens? Automatically, this pair of electrons come on the first oxygen. So what happens? Initially, 2 pair of electrons, now 3 pair of electrons, because a bond means 2 electrons. So and here it was a single bond between second and third oxygen, but now it is between second and third oxygens a double bond. So these two are what? Interchaining structures. So like a benzene, the ozone also shows two resonance structures. Okay, two resonance structures. Resonance structures, these are interconvertible structures by changing position of pi bond with pi bond. We have seen in benzene. Now here what change position of with what is that? Lone pair with pi bond. So whether it is delocalization of pi bond with pi bond, or pi bond with lone pair, or pi bond with a negative charge, the phenomenon is what? Resonance. Is known as a resonance. So based on this, one can calculate the bond order. Bond order means between any two atoms, the number of bonds. So now see here, between these two carbons, what have shown? One line means single bond. If I show between the two carbons, two lines means it is a double bond. Okay, or we can write here it is a triple bond. Means between the carbons we can show triple bond, double bond and single bond. So maximum is a triple bond. Between any two atoms, the maximum bonds is what? Triple bond only, 3 bonds only. So the number of bonds between two atoms in a molecule is called as a bond order. So here, based on the resonance structures, one can calculate the bond order of an atom. So see here, around choose any of the carbon of benzene. Around this carbon, how many bonds are present which are interchanging? How many bonds are present? 1, 2, 3. So the total bonds are 3, and total bonds are 3 around the atom. The total number of bonds by resonance structures. So if I take here, around this carbon 3 bonds are there and the structures are 2. Means here in benzene the bond order is 1.5. Means here you can't say that between the any two carbons there is a double bond is there, or there is a single bond is there. Here the structure is what? Indicating that bond order is 1.5. Means what? It is neither double bond nor single bond. In between the double bond and single bond. So means here collectively we can write that the benzene is having a hybrid structure where the 6 pi electrons, means 3 pi bonds, are continuously changing their position. So here every carbon bond is no more double, no more single. It is having 1.5 bond. So by resonance phenomenon, one can calculate the exact bond order. That is number of bonds between two atoms. And we know that if it is single bond, the bond is single, loose bond. So obviously what we expected, the single bond length is more. So for CC bond it is approximately 1.54 angstroms. For double bond it will be approximately 1.34 angstrom. So here we know that if it is single bond 1.54, double bond 1.34. But here there is no double bond, there is no single bond. So means what? The CC bond length is what here? In between the double and triple bond. That is more than the double bond and less than the single bond, about 1.39 or 1.40 angstroms. Then the same way here in ozone also same thing. That is, if it is a double bond is there, if it is OO double bond is there, the bond length must be 1.48 picometer. Okay, sorry, single bond is there, if the bond length must be 1.48 angstroms or 148 picometer. If it is double bond, it must be 121 picometers. But what is that? The bond length is no more 121 or 148. It is in between these two, that is 128 picometers. Means more length, okay, more length than double bond and less bond length than a single bond. And here around this oxygen, how many bonds are there? 3 bonds. And how many structures are there? 2. So the number of bonds around this central oxygen and the number of resonance structures is bond order, that is once again 1.5. So we can say that in ozone, between any two oxygen, there is no double bond, there is no single bond. Means in ozone, here all the 3 oxygens have same bond order, that is they are 1.5. Along with this one bond, there is half bond. Okay, so this is what known as resonance structure, resonance hybrid structure. And in the same way, we can calculate for any oxo anions also. So I have just done calculation, but yet I have not given you the formula just now. What is that? Based on resonance, one can calculate bond order. So bond order is equals to a formula, simple formula, X by Y. So where X is number of bonds around the certain atom in a molecule and Y is number of resonance structures, or resonance structures also called as canonical structures. But in case of for easy to understand, in case of oxo anions, the Y, which is resonance structures, number of resonance structures, we can take number of oxygens. So we'll see what are oxo anions. What are oxo anions? Okay, so what is this? X is number of bonds. X is number of bonds around an atom, and Y is number of resonance structures or canonical structures in case of what neutral molecules. But if it is oxo anions, means in oxo anions means negatively charged species, we know that anions, if they have oxygen, called as oxo anions. So in oxo anions, instead of resonance structures, it's also, you can take resonance structures also for easy, to make it very easy. It's like a shortcut, because once you know the formula of oxo anion, you can do the calculation quickly. So in oxo anions, instead of number of resonance structures, we can take number of oxygen atoms. Is that clear? So now we'll see the oxo anions. See here, SO4 minus 2 sulfate, SO3 minus 2 sulfite, PO4 minus 3 phosphate. In the same way here, CO3 minus 2 carbonate, like that. ClO minus hypochlorite, ClO2 minus chlorite, ClO3 minus chlorate, ClO4 minus perchlorate. So these are what different types of oxo anions. Now we will take one oxo anion. The simplest one is carbonate. Or you can take one more, NO3 minus nitrate, NO2 minus nitrite. So these are different oxo anions we come across. So now carbonate will take. Now here say carbonate. In carbonate, how many atoms are there? 4 atoms. The central atom is carbon. Around this you have 3 oxygens. And we know that the carbon should have 4 bonds around it, and the charge is -2. So one oxygen is having the double bond and the remaining 2 oxygens having the single bond. So now see here, around this carbon 4 bonds are over. Now we know that oxygen must have 2 bonds. So for this oxygen, 2 bonds, it is satisfied. It is having the what? 2 lone pairs and 2 bond pairs, octet is complete. But in case of these two oxygens, what about they have a lone pair of electrons? Okay, good. But how many valence electrons in oxygen? 6. 6 means it used 1 electron. So 5 plus 1, 6 means 1 electron is odd. And the meaning of minus means what? 1 extra electron. 1 extra electron. So means these oxygens have a negative charge. Oxygens have a negative charge. So this minus 2 means what? Each oxygen is having minus 1, minus 1. Minus 1 and minus 1. So see here. Here, I want some space. So, we'll take a numbering for the oxygens. Say first oxygen, second oxygen, third oxygen. Okay. Now, for carbonate, you have totally 3 structures, means 3 resonance structures, and we have to show the negative charge on each one. Means in first structure we have showed that second carbon is neutral. So now we are going to write a structure in which first or third carbon is neutral, means without charge. So simply write this, no charge, minus, and this is minus. And next, one more structure, that is this time. See, in first structure, the second carbon without charge. In second structure, first oxygen is without negative charge, neutral. And in third structure, we are going to write the third oxygen without charge. So these are what? Resonance structures of a carbonate. So in such molecules, means oxoanions. So what is the formula? X by Y. So what is X? The number of bonds around the certain atom, means central atom in a molecule. So in this molecule, carbonate, see, anion also molecule, because as it is completed its octet, it is stable. So this carbonate also molecular species. So in this molecular species, what is the central atom? Carbon. So around this carbon, what is this X? Number of bonds. How many bonds you can see? 4. And divided by what is Y? The number of resonance structures. Now how many structures you can see here? 3 structures. So 4 by 3. Then you will get its value. So what is the bond order of this 4 by 3? You get 1.33. 1.33. So some students could not write resonance structures. So in this way, what you have to do in that case, just write one structure. Okay. And in that